Hi, this is Physics 2211, Lab 4, Oscillations. Introduction. So the purpose of this lab is to examine the motion of a spring mass system where a mass swings in an arc while also oscillating on the spring, and to compare the predicted and observed motion of the mass. The models and fundamental physics principles used were glow script and tracker, given footage of the experiment, and the energy principles including kinetic, gravitational, and spring energy. The main result preview, so the modeled position versus time graphs were similar to the predicted graphs, and they both oscillated, forming a sinusoidal graph. The main physics ideas and equations focus on energy. Spring energy is shown here, and it depends on the spring constant K and the compression or stretch of the spring S. The kinetic energy is dependent on the motion and velocity and mass of the object. The gravitational energy is potential energy depending on the mass and height. The total energy adds all of the component energies together. We used forces in the coding as well with Newton's second law. The forces in this experiment are gravity and spring. Gravity depends on mass and the gravity constant, and spring force depends on the stretch of the spring, the direction, and the spring constant. We also utilize position and velocity update in order to update the position and velocity of the code. So the system was the mass, spring, and earth. The surroundings, we didn't have anything in our surroundings because we utilized energy instead of work, but we could have done the opposite way, we just chose not to. The initial velocity was 0 meters per second. The initial position was 0.00652, negative 0.705, 0 meters. We also had the gravitational constant 9.8 meters per second, and then the spring constant 6.83 newtons per meter, and then the initial relaxed length 0.7 meters. The procedure, so we utilized tracker and the given video of the oscillating spring to analyze the motion frame by frame, and then frame by frame the motion of the object was tracked in order to create accurate graphs in both the x and y directions. For part 2, we changed the code to reflect the collected data with the initial conditions and then inputted all of the equations like force and energy and etc. so that the code could properly run. Lastly, the data from tracker was utilized to allow the code to compare the predicted model and actual data. This slide shows the tracker data. We tracked it step by step to increase data accuracy from the given video. These graphs show the position in both the x and y directions versus time in SI units. Here's the coding process screenshots. We changed mass, position, and velocity to match the data. We also inputted g, the spring constant, and the relaxed spring length. Then we clarified the variables to input them into the energy equations and position and velocity update. We also clarified the change in energy for the graphs. This slide shows the code's output. It includes the overall change in energy versus time. The other graphs show position versus time graphs. Both graphs have the sinusoidal shapes. Some simulators and differences. So for the x position versus time, the experimental model had much larger fluctuations than the predicted model, but they had the same periods of fluctuation, just different sizes of peaks. The y position versus time, the experimental model had much smaller fluctuations than the predicted model. They also had the same time periods of fluctuation, just the same thing at different peaks and ebbs and flows. The overall energy change remains around 0 because as one energy increases, another energy decreases. It's not a perfect line because it relies on the experimental data. For an overall comparison, the lines for the experimental data are less smooth due to the inaccuracies in tracking the motion. Some possible sources of error. So data tracking, there was a possibility that the data points were not completely in the same spot when tracking the motion of the mass, not completely centered on the object, so that could be a possible source of error. And then within the coding, the lines are not completely accurate with each other, so maybe there could be a slight difference in the numbers inputted for the initial conditions, or the mass could have been weighed wrong. So for some additional questions, is the energy principle satisfied in your model system? Justify this. So yes, our energy principle was satisfied. The energy principle states that the energy cannot be created or destroyed, which is demonstrated in the change in energy graph because the total change in energy is roughly 0. It fluctuates a little bit, but that's due to probably error in the data collection, and this means that as one type of energy rises, another type of energy decreases, and this is in order to keep the overall energy at the same level, showing a conservation of energy. Another question, so they wanted us to make 2 separate estimates of oscillation periods, so by estimating the period of oscillation from the x position and from the y position data, and then compare these and discuss. So to estimate a period of oscillation, you have to utilize the 2 consecutive minimums or maximums and see the time between them. The estimate of the period of oscillation from the y and x position were both 1.5 seconds, so they were both equal. Why is this? Simple harmonic motion describes this because the period is determined by the mass and the spring constant of a system, so it would be the same regardless of the direction of motion. The forces are always trying to restore the system to equilibrium in both the directions of motion we're aiming to do so. Thank you for watching.